Today I'd like to talk to you about my final project for the deep learning class at Harvard Extension School. I chose case study in recognition of emotion from emojis as the topic of my project, and I built a website called EmoSense. Let me give you a quick overview and then jump into the demo. So the problem we are trying to solve is how to detect true human emotions. We developed a deep learning model using TensorFlow and Keras, which can detect true human emotions by analyzing key facial features of micro expressions. The approach we used convolutional neural networks, used deep learning and transfer learning techniques. Technology stack, we use TensorFlow, Keras, Python, GPU, Jupyter, and Google Colab. We used the Kaggle dataset that was used for this compilation back in 2013. The dataset is available here. You can download the data. The results. We built a CNN model which achieved about 65% accuracy. The website to demonstrate the model. Let me jump into that model of the website and show you a few pictures and how it works. So we have this drop zone. You can upload a picture there. Then it would make the prediction for that image, and it would detect the faces, the gender, and the emotion. Try a few images. So far so good. It's detecting pretty good. You can see it can detect multiple faces in the picture as well. Alright, so affective computing is an emerging field of study within cognitive computing and artificial intelligence that is concerned with gathering data from faces, voices, and body language to measure human emotion. This can be used in building human computer interfaces that can detect and quickly respond to an end-user state of mind. There's been publications saying increased demand for facial features and certain software predicted that the global effective computing market will grow from 12.2 billion in 2016 to 54 billion by 2021. Microexpressions are involuntary fleeting facial movements that reveal true emotions or valuable information in scenarios changing from security interviews to media analysis. They occur on various regions of the face and last only a fraction of a second. Universal cultures. The problem we are trying to solve is image classification. So humans have traditionally been able to identify and recognize emotions from people's faces, whether you're happy, sad, or angry. But the computers not so much. Recent advances in the fields of machine learning and artificial intelligence, allowing the computer scientists to create smarter apps that can identify these from sounds, words, images, and even facial expressions. So the goal of our project is to develop a deep learning convolutional neural network model using TensorFlow, Keras, which can detect true human emotions by analyzing key facial features of microexpressions. In addition, we built a website that could utilize this model. This is the website I demoed a little bit earlier. So it can detect the faces using the OpenCV frontal face classifier, can detect whether it's a male or female, and detect the emotions. Kaggle, the overview of Kaggle is a crowdsourced data center computation platform, and there's a great community of data scientists. There's a lot of articles, there's a playground that you can build models, And also there are some rewards, prizes awarded for the winners in these competitions. And there are a number of data sets, public data sets available you could play with. We use Keras, TensorFlow plus Python as our technology stack. TensorFlow is an open source software library for numerical computations developed by Google that supports GPU acceleration. Keras is a minimalist Python library that works on top of Keno, TensorFlow, or deep learning for chain. Keras was developed to make implementing deep learning fast and easy. So we used Keras with TensorFlow GPU backend. Google Cloud released another product that was released recently, and it's a setup-free Jupyter environment, and also they offer free GPU. NVIDIA CUDA and CUDA libraries are widely used in machine learning models because it offers 50 or 100 times faster processing compared to CPUs, especially in image machine. So the neural networks are modeled after human and animal cortex. We'll be using neural networks to build our models. Convolutional neural networks use primarily to look for patterns in an image, convoluting over an image, and it contains several types of layers, from convolutional ReLU pooling, flattened layers, and fully connected layers. Usually these model contains like millions of parameters. Image classification is a problem that assigns labels to a given input image. So in this example here, where it detects whether it's a cat, dog, hat, or a mouse. So we played with a few different CNN models, including Inception, Exception, VGG16, and we found that paper tend to use the mini exception model with a minimalistic exception model inspired by exception or the original exception, and it only contains like 60,000 parameters, and we could save the weights of the parameter in just small as 900 kilobytes file. Okay, let me jump into the code. Okay, so the first step code, of course, is to install the packages. So I'm not going to go over installing GPUs, CUDA, and things like that with literature internet. So especially we'll be using Keras VGG phase and Scalar, so we'll be installing that. And so we created this utility class to load our dataset and reshape it to our proper size. Also, we created this function to split the data between training and validation sets. Data exploration. So we have 7 labels here from entry, discuss, fear, happy, sad, surprise, neutral. And this is the format of our data set. It contains the emotion as integer and pixel 48 by 48 grayscale pixels. Here we can see the categories and the count for each category. So this is the total number of data points we have. And here are some sample images from the dataset. We create this function to pre-process our input. That's a common practice to normalize the data. So then we define this exception model, which is taken from this research paper. So define the model, and here we load the model, and this is the summary of the same model. Next step, you're going to train that model. So here you can see the total number of parameters is just less than 60,000. It's really a small model. So we used data augmentation to increase the number of data points. Um, we rotated the image, we did shift, zooming, shear, and horizontal flip. So here we are training the model over 100 epochs, and the train took like 31 minutes on this GPU. You can see the training and validation accuracy and loss. You can see it's still training really good. It doesn't show any indication of overfitting. So here we are generating our conclusion matrix, and you can see we have pretty good accuracy overall. I'll jump back in here. So overfitting, it took only 30 minutes to 100 epochs, 66, close to 65% accuracy. And the next model we experimented, which gave close accuracy, was the VGG16 model. So what is transfer learning? Why we do that? It's mainly because we don't have sufficient data to train a convolutional neural network from scratch. We need a lot of data to train CNN from scratch, and also it takes weeks sometimes to train CNN from scratch. So these are some of the popular and proven CNN models. So we picked VGG16, which is developed by Oxford University back in 2014 to win the ImageNet competition. And we found this dataset VGG face, also developed by Oxford University, and for the purpose of face recognition. So this is really ideal for use case. So we used VGG face on VGG16 model, and we used the fine-tuning methodology. This is pretty standard. So we train up to block 4 here, and so the first step is we adding our fully connected layer. We fine-tune that, and then we unfreeze convolution block 4 and 5, and then we retrain the whole model, or a very slow learning rate. So here we can see this is the first step, training the fully connected layer, and the second step, training the full model with the fourth and fifth convolution layers unfrozen. Here you can see it's a little bit starting a little bit of overfitting around epoch 40. So we can see it's really around accuracy 66%. So there are some results. So overall, we can see our model performs really well in these images. Conclusions: we got the CNN model with many exceptions to detect human emotions. We got a bit not the CNN model using VGG16 and VGG face dataset. We used TensorFlow, Keras, Python for programming, utilized Google Colab and cloud resources, utilized GPUs for fast computations, and achieved over 65% accuracy. We built a REST API. Okay, let me show you the REST API quickly here. So upload the image, select this one, and you can get the image back. There we go. So, and then we build a website for demonstrating the capabilities of this. Acknowledgements. So this data set was really helpful in building our model. And some of the test images were taken with the permission from scienceforpeople.com. Thank you for watching.